All right, okay. So on our course website on CCLE, I posted some practice problems, okay? This file is called practice final. I don't know if that's, maybe I should say practice problems for the final. I wanted to say it's the practice final itself. Okay, practice problems for the final. Although, you know, it makes this grand claim that if you do well on this practice final, you should do fine on the final. And I'll stand by that statement. But you know, of course, it's going to be different. So anyway, you know, as far as today's review session goes, I want to make it useful for you. So you guys can tell me what you would like to see. So the practice final kind of has all of these things mixed up. Yes, chapter 7 is definitely on the exam as well. But yeah, I posted extra practice problems for chapter 8 and chapter 9. There's also a kind of a formula sheet that gives a summary. There's one thing, we did not do this thing. Confidence intervals, proportions, 2 samples, we did not do that, okay? So everything else is, we've covered though. Confidence intervals, proportion, 1 sample, hypothesis test proportions, 1 sample, hypothesis test proportions, 2 samples. Confidence intervals means 1 sample, confidence intervals means 2 samples. Hypothesis test means 1 sample, hypothesis test means 2 samples. And technically you have hypothesis test for paired data, but paired data, once you find that difference column, it becomes basically means with 1 sample. So anyway, this is a formula sheet. Article questions will also be on there, multiple choice. Yeah, so, all right. Here, let me do a little, and then this practice final is longer than the real final. So it's, so I don't know if I should call it a practice final, but okay. Anyway, here, let's talk about final exam. Okay. Here, you know what? Probably rather than me typing all, writing this out, it's probably better if I type it. Okay. Let's see. Let's make this big. Oh, that's too big. Okay, so we'll say final exam. All right, so it's going to be Friday, 10 a.m. Pacific or 10 p.m. Pacific. So figure out what time that is for you if you're not living in California or in the Pacific time zone, okay? And again, log into Zoom, your camera on, mic's muted. Okay, similar to, and use the same Zoom link for class. And then, okay. So this is kind of what you can expect. We'll say question breakdown. All right, so we're gonna have kind of definition / conceptual questions from chapters 7 to 9, okay, covering confidence intervals and hypothesis tests. So probably like 7, 8 questions. And then we'll also have maybe kind of around 3-ish questions from the journal article. Okay, and then maybe around 3 questions or so covering conditions to use the central limit theorem. Let's see. Would questions regarding the article be more conceptual, or would they be extremely specific, like asking us for the specific answers to each of the worksheet questions? Well, they will be specific related to that particular article. So from the assigned journal article. So that particular article, I'm not going to give you a new article to read or something. So it'll be that one particular one. I don't know how much more I can reveal about the nature of those questions. Okay. And then, you know, probably 7 questions or so for definition, as conceptual questions from chapters 1 through 6. Okay. And then, let's see, let me count these 10. Yeah, 20. Okay. And then about 20 questions. So 20 to 25 questions that are like calculation-based questions from chapters 7 through 9. Okay. And this will be kind of some. I've provided lots of practice problems. Okay. So about half of the test will be kind of these calculation-based questions, but then the other half will be, you know, more definition conceptual. Okay. And I've given a small handful of conceptual questions for practice regarding, all right, so I'll say C, conceptual practice. I guess study the reading assignment. Okay. This is in practice final. Conceptual questions from chapters 1 to 6. I have no practice provided for this. And then lots of practice problems. You have chapter 8 practice, chapter 9 practice, and then practice problems. Okay, so this is kind of the question breakdown. That's what we got. You're looking at around 40 to 45 questions, and you got 2 hours to cover. These are estimates. You get a little, so something around here. I don't want somebody to go through the final and check off and say, oh, you asked 8 questions here. Or you only asked 2 questions here. So it's something around there. Okay. But this is kind of what you can expect. And then everything is multiple choice. Which, you know, pros and cons to multiple choice exams, but that's what we'll have. Okay, just any questions regarding content or the breakdown? No? All right. Okay. I guess I'll save this. Where should I save this? This. Stats 10. Final exam topics. Post that. Okay. All right. Well, I guess I can work through some of these problems, and we can talk about them. And I'll, I guess maybe I can post the answers up as well for each of these things. Will you need? Okay. So questions. Are these estimates or exact amount of questions? Yeah, they're kind of estimates. Okay. How many decimal places will I want you to use for the calculations? Well, it's multiple choice, so I would say keep the. Generally, I say keep around 4, and then find the answer that matches closely. So probably the answer choices will probably be rounded off a little bit. But you know, generally I would say keep at least 4 decimals in between, and then round off at the end. Will you need R for the final? I don't have any R specific questions, but your calculations can be assisted by using R. You're not forbidden from using R, but you know, I would say you can complete the final without using R at all. If you want to use R, you're allowed to. So I guess that's that. So okay, well, let's all right. Okay, so any questions about this? All right, let's go ahead and take a look. So you know, regarding the calculation-based questions, it will be similar to kind of the setups that I have here, where I kind of, you'll see in these practice final exam and chapter 9, the chapter 8 practice, what I have is I've got, you know, I will give some kind of scenario with a little bit of data, and then, you know, that paragraph will usually end, you know, does this provide evidence of something, something, something? And then I'll have questions related to it. So probably like, probably on the final, you can expect maybe 6 different scenarios or so, and each of them will probably have maybe around 4 questions associated with each one, okay? And, you know, the questions will be something kind of like, you know, what would be the appropriate hypothesis for this problem? What would be your standard error? What's your p-value? What's your conclusion? Things like that, okay? So you can see, you know, for this problem, I give a description of the data, and then I say what would be the hypotheses, what's the standard error, what's the test statistic, what's the p-value, what's the appropriate conclusion. So that's one example. Chapter 9 problem is very similar. I give something here, what would be the hypotheses, standard error, test statistic, p-value, and conclusion. Very similar kind of setup throughout the final. Practice final, and for the practice final, I gave you know, a lot. So there's how many of these? 1, 2, 3, 4, 5, 6, 7, 8. eight of these scenarios, okay? And each of those have maybe 5 or 6 questions. So the practice final is a lot, maybe not a lot longer, but it's a little bit longer, maybe about 25-30% longer than what the real final would be. You can still expect some kind of similar setup where you're going to have a question and then maybe around 4 questions associated with it. Okay, so I guess what I'll do is I'll start looking at. We'll look at this practice final together, and we'll just kind of run through these questions. And if you want me to slow down or talk a little bit more in depth on a certain topic, I'm happy to do that as well. Okay, this review session is for you guys. So you know, if something I'm doing is not a good use of your time, let me know, and I will happily do something different. Okay. All right. So so here, let me just show you there's, you know, you'll have maybe around three of these types of questions, okay, where I'm going to ask for checking, are the conditions for the central limit theorem met, okay? So you had similar problems to this in the homework, but I never gave you like a quiz or anything like that, right? So okay, so let's so this will be from the practice final. We'll say checking central limit theorem questions, conditions. Okay, so let's do number 1 here. All right, so here it says a study is performed to understand the relationship between bright lights and headaches. 80 randomly selected subjects are exposed to bright lights and 20 complain they experience headaches. 90 randomly selected subjects are exposed to less bright lights and 20 complain about headaches. Or 12 complain about headaches. Are any conditions violated? You know what? Let me do this. So we'll set that right there. All right, okay. So when we check conditions, we actually have a few. These are the conditions that we can check. Violates. These are your answer choices here. Okay. So so as far as A goes, does independent and random. Okay. So here it says randomly selected, so this condition is met. So we are not in violation of this. Okay. All right. Big population. Actually, it's a little bit out of order here. But okay, so the big population states the population needs to be 10 times bigger than the sample, right? Check. Okay. And so our population would be kind of like anybody who might be exposed to lights. So that would be pretty much everyone. So that's like, so that this condition should be met, okay? All right, and then large sample condition. Okay, so what we need here, we have 2 samples. And we need 10 successes and 10 failures in each sample. So a success would be anyone who answers kind of yes, and the failure would be anyone who kind of answers no. So here we've got 80, and this is kind of basically we have 20 yes, which means we're gonna have 60 no. Okay, and then both are greater than 10. So that's good. Okay, and then the other one we have 90 subjects, and we have 12 yes and 78 no. Okay, 78 being 90 minus 12. Okay, and both of these are greater than 10. So that's also met. So this condition is also met. Okay. All right, so all conditions are met, does not violate any. So the answer is D. Oh dear. Okay, something happened. Okay, so the is D. No conditions violated. Let's figure this out here. Okay, so this would be. Okay. Let's try. Let's just keep moving on here. All right. So researcher makes a confidence interval for how common a certain disease is in the U.S. population. All right. He finds 300 randomly selected subjects and finds 2% of them have the disease. Are any conditions violated? Okay. So independent and random. That's met. Okay. Randomly selected. So yeah, well, I'll work through some of these here, and then I'll post the answers to CCLE as well. Okay. Okay. Big population is the U.S. population, and we selected 300. So 300 times 10 is 3,000. U.S. population is bigger than that, so we're fine. Okay. Large sample. Okay, we need at least 10 yeses and 10 nos. Okay. So the large sample condition, if we do n times p to kind of get how many yeses, so we have to do 300 times 0.02, we only have 6, okay? This is not bigger than 10. Okay, so the large sample condition has been violated. Or large sample condition has not been met. Okay, so our answer is going to be answer choice C. Okay, on the final, will there be one correct answer? Yeah, we'll just keep it to one correct answer each. Okay, let's see if we can do number 3. Here, why don't you guys try out number 3? Okay, a UCLA student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds data from 100 people and find that 45 of them answered yes to his questions. So are any conditions not met here? All right, so we want random and independent, big population, large sample. Okay, and the answer is, yeah, it is not random, right? So we're just interviewing people he meets. That's not going to be random. This that thing is not going to be a random sample. Okay, the other ones, the other conditions are met. Okay, so big population. You know, if we're going to UCLA campus is our population, UCLA student body. It's big. It's like, I don't know how many people, 40,000 something. Lots of people, okay? Large sample, we sampled 100 people. We got 45 yeses, which means we have 55 no's. That's over 10 for both, but it's not non-random, okay? Just going around meeting people on the people who walk around, that's not going to be a random sample, okay? You're going to get a sample that favors people who go outdoors and walk around, okay? Which, you know, a lot of people, not everyone does that, right? Well, especially today. But okay, all right, let's do one more of these things, all right? Okay, so anyway, you're gonna have a few questions like this, right? Company wants to survey its employees. It has 800 employees. It selects 100 of their employees, randomly interviews each of them, asking if they have negative interactions with their coworkers. 25 of them answered yes. Are any conditions violated? Okay. And so I should just, okay. So what do you guys think for this one? Yep. Okay. So we'll say big population. This is not met. Okay, right? The population is equal to 800, and our sample is 100. And then 100 times 10 is 1,000. And, you know, so, you know, we have sampled too many people. I'm having a hard time writing. Okay. All right, you guys got it. Okay. I guess that's it then for these types of questions. I guess maybe we'll go we'll do conceptual practice questions, I guess. Oh, you know what? I'm sorry. One of these questions, I never gave you the. I gave you I put in a question here that we did not cover. Okay, so don't so skip number 2. But okay, so let's go ahead. We'll go. We'll do these first 3 questions, and we'll skip question 2. Okay, so this one. I mean, I'll give you the answer, but this was not covered. Data not covered in class. Not hard, but it would be unfair for me to put that on your exam. Okay, so number 1 says, and obviously these are not going to be the exact same questions that appear on the final, but this will give you at least a little taste of what you might be able to expect, right? Okay. So number 1, we've got the, all right, so I like this, that you guys are putting your answers in the chat, but you know what we'll do is I'll have you guys hold off. I want you to think of your answer. We'll give everybody like a few seconds to think of your answer, and then you can throw your answers in the chat, okay? Or you know what? This is what we'll do. We can have everybody go on their participants panel, and we'll turn these buttons into answer choices. Okay, so if you think it is A, you'll click this. B will be the no, go slower will be C, and D will be the go faster button. Okay, so we can do it that way. And this will be kind of like a, it's like when people have surveys on Facebook or something. Okay, all right. Significance level alpha is used to decide whether or not to reject the null hypothesis. What else is alpha equal to? Okay, so go ahead and think of the answer. So read your answer choices, A, B, C, and D. Think of your answer, and then and we'll say, and I'll tell you when to reveal your answers on the chat window, or the I'm sorry, the participants window. So participants window. Okay. All right. So you've got probability of mistakenly rejecting the null hypothesis when the null hypothesis is true, correctly rejecting the null when the null is false, correctly rejecting the null when the null is true, mistakenly rejecting the null when the null is false. Okay. All right. Go ahead and let's put in your answers. What do you think? A, B, C, or D, meaning yes, no, slower, faster for A, B, C, or D? All right, yeah, okay, great. Yes, the answer is indeed A. Okay, this is it. All right, so alpha is equal to the probability of type 1 error. And as you guys have correctly answered, type 1 error is the false positive which is mistakenly rejecting the null when the null is true. Okay. We didn't cover this in class, but beta is equal to the probability of a type 2 error. Which is the false negative. And that would be answer choice D, okay? But I won't put that on the final, okay. Okay, what is a type 1 error? Okay, this is like almost the exact same question as question 1. So it is that we are making a false positive, so that's mistakenly rejecting the null, and it's a mistake because we rejected the null when we shouldn't reject it, meaning that the null hypothesis is true, right? So B is mistakenly rejecting the null when the null hypothesis is true. So we don't want to do that. Okay, let me have you guys look at number 4, all right? And we say, imagine a criminal court case with the following hypotheses. The null is that the defendant is innocent, and the alternative is that the defendant is guilty. And based on the way that the American justice system has been created, which, you know, we recognize has not fully been realized, but this is the kind of the system that we strive for and hope for. Do we want a large alpha or a small alpha? And okay, so go ahead and think of your answer. Think of your answers. Is the type 1 or the type 2 error worse? And based on that, do we want a large alpha or small alpha? Think about that, and then in a moment I'll have us all kind of click the yes, no, slower, or faster buttons for A, B, C, or D. Okay, and so, you know, to kind of, what is a type 1 error versus a type 2 error? Okay, so go ahead and reveal your answer choices. What do you guys think? Okay, so we've got different answers going on here. All right. Okay, and the answer is D, that the type 1 error is worse than the type 2 error, so we want a small alpha, okay? So the type 1 error, this is the false positive. This is innocent person is convicted. So someone is convicted for a crime they did not commit. We don't want that, okay? The type 2 is the false negative. This means a guilty person is let go. Okay, we also don't want that, but okay, so we don't want that either, but we will we would prefer to avoid the type 1 error, or the type 1 error is worse, okay? All right, and because alpha is equal to the type 1 error, we want to minimize the probability of type 1 error, so we want to have a small alpha, right? So alpha is equal to the probability of the type 1 error, so we want to make this as small as possible. We want a small alpha. Okay, so we've got that. So we'll go ahead and keep going here. Again, that's your answer choices A, B, C, and D. Okay, let's look at questions 5 and 6. I guess we'll do 7 and 8 as well. Okay, and again, so we'll go through and we'll pick our answer choices here. All right, so imagine a doctor diagnosing a patient. The patient undergoes some tests to detect cancer, and we have the following hypotheses. Null is that the patient has no cancer, is healthy, and alternative is that the patient has cancer. And what would a type 2 error be in this scenario? Okay, so go ahead and read through the answer choices, and then in a moment we'll go through and pick our answers. Okay. We have a question. Increasing alpha would increase the risk of type 2 error. Actually, increasing alpha increases the risk of type 1 error and would actually decrease the risk of type 2 error. So this is just a side note. Increasing alpha increases probability of type 1 error. Okay. And with everything else equal, decreases type 2 error. Okay, go ahead and give us your answers for this scenario. What would a type 2 error be? All right, so the type 2 error, this is the false negative, okay? Which in this case means the alternative is true. Patient actually has cancer, but we don't reject the null, okay? So the alternative is true. but we do not reject a null, okay? So as far as this problem goes, it's going to be we believe the patient has no cancer, okay, even though the cancer actually exists in the patient's body. Okay, so that's going to be answer choice A. All right. Okay, good. All right, so the ones who are participating and clicking the buttons, you guys are doing great. So thank you, and I hope this feels reassuring at least. And those of you who aren't clicking, that's also okay. I hope this is helpful, and you guys are learning from it. Okay. All right, so when we use a two-sided alternative, meaning we've got a not equal sign in the alternative hypothesis, this means that, okay, the p-value, okay, and your answer choices will always be double if we use a greater than sign, will always be double if we use a less than sign, or it might be greater or smaller than the p-value of a one-sided alternative depending on the direction of the alternative. All right, so go ahead and think about that for a few seconds. And all right, okay, go ahead and pick your answers. What do you guys think? People seem to be a little bit more hesitant with this one. Are you guys able to see each other's statuses, or is this just like a secret thing that only I can see? With, are you guys able to see what other people are clicking, yes or no? Or, okay, you can see everyone's. Okay, all right. Okay, the answer is indeed C. Might be greater or smaller than the p-value of a one-sided alternative, depending on the direction of the alternative. Okay, so this, it is possible, okay? So a lot of times, you'll have a picture, right? And then the one-sided alternative might look like this. So if this is, the alternative has a less than sign, right? And if the alternative has a not equal sign, it will look like it's, this is like a terrible picture, it'll look like it's double, okay? So a lot of times it is double, but it's also possible, okay? You could have the quote unquote wrong direction. And in that case, if you have a alternative hypothesis in the wrong direction, okay? Like if you have, like let's say your null is p is equal to 0.4, and then the alternative is that p is less than 0.4, but then your p hat comes in at 0.5, right? 0.5 is going to be higher than 0.4, and because your alternative has a less than sign, you're going to take everything that's over here, okay? Whereas if you had a two-sided alternative, you could have p not equal to 0.4, and then if you have p hat equal to 0.5, if your data comes back or it's like this, you'd have to check 0.3, 0.4, and 0.5, okay? All right, and so, you know, in these scenarios, yes, the alternative, the two-sided alternative is going to be double the one-sided alternative. But in these scenarios over here, the two-sided alternative may be greater or smaller than the one-sided alternative, and we're not quite sure. So, so the answer is C. Okay, depending on the direction of the alternative, of the one-sided alternative, the two-sided one could end up being more or less. All right. Okay, let's look at number 7. It says you perform a hypothesis test for proportions with one sample. The alternative states that the population proportion P is greater than 0.3, and you find that your p-value is greater than alpha. All right, so here you've got the null hypothesis and the alternative. The alternative states that p is greater than 0.3, which means our null hypothesis, well, p is equal to 0.3, and then whatever my p-value is, it turned out to be greater than alpha. Okay, so when we get something greater than alpha, that means we do not reject the null hypothesis. Okay, and our null hypothesis states that p is equal to 0.3. So, so what do we say? We are going to say answer choice A. We do not have evidence that the population proportion is greater than 0.3. Okay, we can never say that the population proportion equals 0.3. The sample proportion, well, we would never make a conclusion about the sample proportion. We probably have evidence that the sample proportion is something, some particular value, but that's not, we can't infer that from the statement here. And we have evidence that the population proportion is greater than 0.3. This is not true. This would be true if our p-value is less than alpha. All right, and then for number 8, it says you perform a hypothesis test for population means with the alternative hypothesis that the two populations have different means. With alpha equal to 0.05, the test reveals that you would reject the null hypothesis. If you had done the same test with the same data, but this time used alpha equal to 10%, what conclusion would you have made? Okay, so let me have you guys think about your answer choice for number 8, and then after you think of your answers, I'll have you guys all click what you guys, your response. All right. Okay, what do you guys think for number 8? All right, so we've got some people with A, some people with C. Okay, so what can we say here? So we've got alpha equal, initially we have alpha equal to 0.05, and it says that you would reject the null, right? So you would reject the null means our p-value is less than alpha, okay? So we don't know exactly what it is, but we do know right now that our p-value is less than 0.05, okay? Even though I don't know exactly what it is, just from this, we know our p-value is less than 0.05. Okay, so if I do the same data with the same test with the same data, I would get the same resulting p-value, same resulting test statistic, all of that. This time, if I use alpha equal to 10%, right? So is this p-value less than 10%? Okay, And the answer is yes. Okay, even though I don't know exactly what it is, I do know that my p-value is less than 0.05, and I can also say it's definitely less than 10%. Okay, if I had said if alpha is 1%, then the answer is we don't know. Okay, if we said if alpha is 1%, okay, is this same p-value less than 0.01? The answer is we do not know. Okay, all right. So that's like a little taste of what kind of questions you can expect for the conceptual section on the final. Okay, it's not going to be, it's not obviously not going to be exactly the same, but it'll be a little bit like that, all right? So so what did I say? All right, so we've got questions covering the central limit theorem, conceptual questions from chapters 7 through 9. So that's kind of what we've covered. Okay. The journal article, you guys should have gone over that in your discussion or lab section, so I'm not going to do that here. Or I don't know if you guys had any questions from the journal article reading that you want to ask me. But you'll have a few questions there. Okay, and then I guess there's technically a couple practice questions from chapters 1 through 6 at the very end of this practice final thing. I think I put some here, right? A bar chart's used for what kind of data, you know, a normal model, what's within 2 standard deviations of the mean and things like that. Okay, so there are actually a few questions here. Okay, I guess I can start doing some of these calculation-based questions. Or did you guys have anything else that that you want to see covered or done? No? Okay. Then I'll copy these here. We'll work through this. Okay, and then I guess after this we can take a short break, and then we can just keep kind of moving through the practice questions that I've provided. All right, so here it says a farm wants to test 2 different diets for their cows to see which diet causes more weight gain. They randomly select 10 cows to give diet 1, and they select 12 cows for diet 2. And after 2 weeks on diet 1, the 10 cows gained an average of 15.2 with a standard deviation of 4.1. After 2 weeks on diet 2, the 12 cows gained an average of 12.6 with a standard deviation of 3.4. And the following questions refer to a 95% confidence interval for the difference in average weight gain, diet 1 versus diet 2. Okay, so we are dealing with means, right? Because we're talking about pounds, not proportions. Okay, so we've got means. And then, and it talks about confidence interval. So we're gonna do confidence interval. And how many samples do we have? And are they paired or are they independent? We have 2 samples. Okay, because we have diet 1 and diet 2. And if we look at these, the measurements for diet 1 and diet 2, they can't be paired with each other, okay, because we've got 10 cows over here and 12 cows over here. So they're 2 samples and they're independent. Okay. So you know what? I'm actually going to just go ahead and just copy some of these formulas over. Okay. So if you're going to make a confidence interval for means with two samples, this is basically it. Okay. All right, so our interval is x bar 1 minus x bar 2 plus or minus t star times the standard error. And the standard error is this formula right here. Okay, so what value goes in the center of the interval? The center of the interval is basically the part before the plus or minus. Okay, so as far as number 5 goes, that center part is x bar 1 minus x bar 2, which is going to be 15.2 minus 12.6. So at the center of the interval, we're going to put in the number 2.6. Okay. What do we use for t star? Okay. So for number 6, t star, well, our degrees of freedom is going to be equal to n minus 1. And we have two n's, right? We've got 10 and we have 12, right? So we have n1 equal to 10 and n2 is equal to 12. We're going to use the smaller of n1 and n2. So our degrees of freedom is going to be, we've got 9 degrees of freedom. Okay, so we're going to look up, I need my table. Okay, so 9 degrees of freedom and 95% confidence, we've got 2.262. Okay, so we got that. The value of the standard error, okay, standard error, that's just plugging in all of the values here. We've got S1 is 4.1 squared over N1, which is 10. And S2 is 3.4 divided by N2, which is 12. Okay, so let me get my calculator out. Yeah. Okay. All right, I don't know what happened. My computer is stuck. Oh boy. Okay, well, you'd have to punch that into your calculator and get something. What's going on here? Oh dear. Okay, well, we can put this into R. Didn't want it, but, oh, there it is. Oh, okay, so it did. Okay, well, anyway, so on my calculator, I can just do 4.1 squared over 10 plus 4 squared over 12. What's that? 1.626. Okay, and make a 95% confidence interval. So we're going to have 2.6 plus or minus 2.262 times 1.626. So we're going to have 2.6 plus or minus, multiply this, 1.626 times 2.262. So 2.6 plus or minus 3.678. So, 3.68, sure, okay. So that gives us 2.6 minus 3.68. negative 1.08. And then if I change that to plus, 6.28. Okay, based on your confidence interval, do you conclude that there's a difference in the average weight gain, right? So we're looking for is 0 in the interval. Okay, and the answer is yes. Okay, so we're going to say 0 is within the interval. So we do not have evidence that there's a difference. Okay, and then lastly, if we make a 90% confidence interval, how would it compare to the 95% confidence interval? Okay, so a 90% confidence interval will be narrower than a 95% confidence interval. Okay, because because what we would be doing is we would use the 90% thing, which is a smaller t star. The standard error is going to remain the same, but our t star will go from 2.262 to 1.833. So we would get basically the margin of error would be a smaller number, right? Instead of 2.262, we're multiplying it by a smaller number. So this thing, instead of 3.68, will be a smaller value. We're going to get a smaller margin of error. Our interval will be narrower. Okay, can I show you how to do this calculation in R? Sure, we can do it in R as well. Okay, so I mean, there's all sorts of ways you can do this, but you can do square root. Inside the square root, I'm going to do 4.1 squared divided by 10 plus 3.4 squared divided by 12. Okay, and I guess I can. You can just type that in for the square root. Okay, so we get the basically the same answer there. So so the squaring is shift number 6 for a square, 4.1 squared, and then you divide by 10, 3.4 squared divided by 12. So R respects order of operations, so it's going to do the exponentiation before the division. So it's not doing 4.1 raised to the 2 tenths, 2 over 10 or something, like to the 0.5. It's going to do the exponentiation before the division. Okay, but and then it does the exponentiation before the division, and it does that before it does the addition, right? So R respects kind of PEMDAS order of operations. All right, is this feeling all right? Why don't we go ahead and take a 5-minute break here, and then we'll come back, and then we'll do a few more of these problems. And again, I'm happy to, if you guys come up with other questions that you have, or if you want to just look over some of the things and say, I want you to try this one out, we can do that as well. Okay, so we'll go ahead and take a 5-minute break here. Okay, so so we have, all right, so we'll keep kind of clicking through here. So I've given you like a lot of practice problems. You don't need to do them all, okay? I mean, some people like to do as much practice as they can, and I think that's a good way to study. But if you feel comfortable without it, then you feel comfortable. Okay, obviously study as much as you feel necessary. Probably the more you study, the better you'll feel prepared, which is always a good feeling. Okay. All right, so let's look at this. Ruler and yardstick factory machines suspected to be defective. The yardsticks it produces should be exactly 3.0 feet long, and you measure a sample of 40 yardsticks and find that the average is 3.02 feet, with a standard deviation of 0.03 feet. Okay. Is this evidence that the machine is producing yardsticks that are too long? Yeah, it seems like it, huh? Okay, so here, is this a one-sided or two-sided test? Okay, and so the fact that we've got too long, this is going to be a one-sided test. Okay, so for 12, it asks, what would our hypotheses be? All right, so again, here, what's important, are we dealing with proportions or means? Okay, so we've got, we're dealing with means. We've got the mean length of the yardstick, okay? And we've got one sample, okay? Just one sample of 40 yardsticks. And we're doing a hypothesis test, okay? One sample, and it's a hypothesis test, okay? So, so anyway, our null hypothesis, when it's about a mean, is always going to be about mu, okay? And we want mu to be exactly 3.0 versus the alternative that the length is too long, so it's going to be greater than 3.0. So that's going to be our null and our alternative, okay? All right, what is the value of the test statistic? Okay, so T, our test statistic, is going to be, x bar minus the mean divided by the standard error, okay? Our standard error is s over the square root of n. So that's going to be 0.03 divided by the square root of 40, which is 3 divided by square root of 40. Okay, that's 4.7 times 10 to the negative 3. Let me change my setup. I don't know. Okay, 0.00474. Okay, so that's a pretty small number. Okay, all right, so my test statistic T is going to be 3.02, that's my x bar, minus the mean, that's from the null hypothesis, 3.0. This is divided by the standard error of 0.00474. Right? I did this correctly, right? Standard deviation 0.03 divided by the square root of 40. Okay. All right, so what is this? This is going to be 0.02, 3.02 minus 3.0 divided by 0.00474. And this gives me 4.219. Okay, so that's my test statistic T, okay? So find the p-value. So there's a couple ways I could do this, right? So the answers that I'm going to provide will align with basically what happens if you use the table, but if you don't want to use the table, you can look it up in R as well, okay? So, so we have n minus 1 degrees of freedom. So we have 40, so we have 39 degrees of freedom. And so I'm just going to go to the table, and I'm going to use kind of, we can look at 30 or 40 degrees of freedom, okay? And our value test statistic is 4.219, which is greater than kind of the last column, 3.385, 3.307, okay? So 4.219 is beyond 3.307. So the tail area, so the tail probability is going to be less, right? Because we're going, remember, this is how much is left over in the tail. And as we get farther and farther away from 0, we're going to have less and less in the tail. So our tail area is going to be less than 0.001. than the column heading of 0.001. Okay. Alternatively, I could come over here and ask for PT of 4.219 using df equal to 39. Okay. And it gives me this, so I can do 1 minus that. Okay. And it tells me it's 7.07 times 10 to the negative 5. Okay, so this is kind of unfortunately, this is when it's really small. R produces it in scientific notation. Okay, this is what beyond 3.307, which is kind of the last column in the T table. Okay, and so here we have 7.075 times 10 to the minus 5, which would be, you move this over 1, 2, 3, 4, 5. So it's 0.00007075, okay, which indeed is less than 0.001. Okay, so with number 15, if alpha is 0.05, what's your conclusion? Our p-value is less than alpha. Reject the null hypothesis. That means we have evidence that the yardsticks are too long. Okay, and then number 16 says, if the conclusion you made was wrong, what kind of mistake did we make, right? So if the conclusion is wrong, then we would have made a type 1 error, right? Because we rejected, if our decision to reject the null hypothesis is wrong, then that's a type 1 error. Okay, can you explain why we subtract from 1 regarding this getting our p-value here? Okay, so the thing is the table, or when you use R's kind of t-table thing, okay, built-in t-table, this thing always gives you the area to the left, and in our case we want, so our picture, R always gives you the area to the left, right? So what we have is, we're centered at 4 and we're over somewhere at 4.219. And what we want to know is, we want to know this. This is what we want to know. This is going to be our tail area. This is the tail area. Okay, but R always gives the area to the left. Okay, so this area over here is 0.9999293. Okay, and we don't want that. Okay, we don't want 0.999. We want this area, which is going to be 1 minus 0.9999293, which is equal to 0.0000707. Okay, all right. But again, you don't actually need to look that up. I mean, if you can make the same conclusion just by saying, oh yeah, my number is bigger than 3.3. I'm just clicking along here. If you want something different, let me know. All right, so it says researchers believe that 14% of the population is left-handed. A local school decided to see if their students have a different proportion of left-handed people. The school has a total of 1,500, and they randomly select 90 students for the study, and they find that 15 of them are left-handed, as evidence that the proportion of left-handed students is different from the population proportion. Okay, so 17, what's the sample proportion? All right, so first of all, what we are dealing with here is we're dealing with proportions. And here we only have one sample. Okay, and here it says we're making a confidence interval. So we're gonna make a confidence interval. Okay, so number 17, this is really easy. This is p hat. This is our sample proportion. P hat is 15 divided by our 90 students. Okay, so 15 over 90 is like 0.167. 0.1667, 0.1667. Okay, you want to make a 90% confidence interval. Okay, what critical value z star would you use? Okay, so for a 90% confidence interval, you just kind of need to look at your table. Okay, and that's going to be 1.645. I actually provide these in this kind of the formula sheet. 80% is 1.28, 90% is 1.645, 95 is 1.96, and 99 is 2.58. So these are provided here. Again, we're not going to use this thing. Confidence intervals with two samples, proportions. I didn't cover that, so that's not going to be here. But this is what we have here. I guess I can copy this. All right, so when making a confidence interval, what's the standard error? Okay, standard error, so number 19, the standard error is the square root of p hat times 1 minus p hat divided by n. So I've got 0.1667 times 1 minus 0.1667 divided by n, which is 90. And we take the square root, okay? So just be careful. Make sure you identify these numbers correctly, right? And so here there is 1,500. This number here is just to throw you off, okay? And make sure you divide by 90, not 15. N is equal to 90. Kind of your x is 15. Okay, so you want to divide by 90. Okay, if you divide by a different number, you're going to get the wrong answer. All right, so let's go ahead and do this. So we're going to do 0.1667 times 1 minus and we're going to divide by 90. Okay, and I get 0.0393. So that's my standard error. Okay, what will be the center of the interval? The center is going to just be p hat, so 0.1667. That's the part in front of the plus or minus. So number 21, go ahead and make the confidence interval. So you're going to have 0.1 p hat, 0.1667 plus or minus basically z star times the standard error. 0.1667 plus or minus 1.645 times 0.0393. 0.1667 plus or minus whatever this is. So I take that and I multiply that by 1.645, 0.0646. All right, so let's go ahead and try this out. 0.1667 minus 0.0646, and that gives me 0.1021. And then on the other hand, we'll add this, and we get 0.101. Wait, that's not right. There we go, 0.2313. Okay. Is this evidence that the proportion at the school is different from the nation? All right, so what is the nation? The nation is 14%, okay? So 0.14 is inside the interval. Okay, so we do not have evidence that the school's proportion is different from the nation's proportion. All right. We feeling okay? Should I just keep going? I don't know. All right. No one's saying anything, so so if the nation's value was outside the interval, we would have evidence of difference? Yes. So if the nation, so our school's proportion was like around 16, 17%, right? 0.167. So if the nation, and when we made the interval, it was like from 10% to 23%, okay? If the rest of the nation was like 9% left-handed people, okay? Then our school's proportion of 16%, or the sample of 16%, is different enough from the national percentage of 9% that we would say we have evidence that our school's proportion is different from the nation's proportion, right? So the fact that we got 16 or 17% in our sample from the school is kind of so different from what we would have expected. If the nation was only 9%, we would not expect to get a sample where our sample is like 16 or 17%. So the fact that we got 16 or 17% would provide evidence that our school's proportion is different. Okay, here it says you buy a bag of Starburst candies and Jolly Rancher candies. And the bag of Starburst candy contains 80 pieces, and 12 of them are cherry flavored. And then the Jolly Ranchers has 70 pieces, and 14 of them are cherry flavored. All right. So assuming these are kind of truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? All right. And so this is what we have. Group 1 is 80 pieces and 12 are cherry. And group 2 is 70 pieces and 14 are cherry. And we're going to do a hypothesis test. Okay, so here we've got proportions. We have 2 samples. And we have a hypothesis test. Okay. You know, I'm going to go ahead and I'll copy the formulas from this thing. So this is what we've got: hypothesis test proportions, 2 samples here. All right. So write the hypotheses. Okay. Okay. So the null hypothesis is that the 2 proportions are equal to each other. P1 is equal to P2. And then the alternative is that they are different. Okay, so we're looking at, are they different? So we're going to say P1 does not equal P2. All right, so for this hypothesis test, what's the value of P hat? So P hat, so 24, P hat is the overall proportion. Which is kind of x1 plus x2 over n1 plus n2. So this is kind of like what proportion total are cherry flavored. So we're going to have 12 plus 14 on top, and on the bottom, I'll have 80 plus 70. So this is kind of like a the overall proportion. So we've got 26 divided by 150. I don't know what that is. .1733. Okay, so that's our overall proportion p hat, 0.1733. All right, do the hypothesis test. What's our test statistic? Okay, our test statistic z is going to be p hat 1 minus p hat 2. Okay, so p hat 1 is 12 over 80. I think that's 15%. Oh, no. No, wait, I typed that in. 12 over 80, yeah, it's 15%. And p hat 2 is 14 over 70. That's 20%. Okay, so we've got p hat 1 minus p hat 2 over the standard error. Okay, so p hat 1, and let's do our standard error calculation. Standard error is going to be 0.1733 times 1 minus p hat. 0.1733 times 1 minus 0.1733 over 1 over n1, which is 1 over 80, plus 1 over n2, which is 1 over 70. .1733 times minus 733. It says, this one messes me up sometimes because my notes had two ratios with the same denominators. So I forgot how to do it with 2. Wait. A numerator? Wait, hold on. 1 over 80 plus 1 over 70. Yeah. Did I do something? Did I do something wrong? Sorry.
No, I'm confusing myself. So my notes for this one, I had the two samples both had the same sample size. So, and when I calculate the standard error, like I forget how to do it with where there's two sample sizes. Does that make any sense?
Yeah, so you're going to have 1 over, you just used the two different numbers. Well, okay, so here's an example where we have two different sample sizes. One is sample size 70 and one has a sample size of 80. So, so I'm just kind of plugging in the numbers exactly as I see them.
Okay.
And when I do the calculations, I get 0.06195. If you wanted to do this in R, you know, it's.
Yeah, I've got it written out in R, and it's like just using in instead of.
Yeah, so I got 0.1733 times 1 minus 0.1733 times. So with R, you have to put in the multiplication sign. So 1 over 80 plus 1 over 70, and this should also, yeah, this gives us the same.
Cool. Got it.
Same number here. Okay, so.
Thanks.
You know, I don't know if this is any.
No, it's
any easier. to see, but I'll put this right here as well.
Awesome, thank you.
Okay, all right, and then so my z-score here, I've got p hat 1 is 0.15 minus p hat 2, which is 0.2, divided by my standard error of 0.06195. Okay, so this is basically 0.05 divided by this number, right? So I'm going to do, or negative 0.05 divided by, whatever answer I had earlier. And I get negative 0.807, negative 0.81. Okay, so, so this is my test statistic. Z is equal to negative 0.807. And then for the p-value, we have to look this up in the table, right? And we want different. So because it's two-sided, I'm going to go to negative. The table only has 2 decimals of precision, so we're going to look up negative 0.81 and find the area to the left. And then we're going to also multiply it by 2. So the total p-value is going to equal 2 times whatever this tail area is of negative 0.81. So I go, I have to look up the z table here. Look up negative 0.81, 0.2090. So this is 0.2090. So my p-value is 2 times that, so I get 0.418. Okay, so that's a very big p-value. I mean, we could have also gone to R and looked up, p norm of negative 0.81, and that gives us, 2.09, and we multiply that by 2, get, 4.18, 4.179, something right around there. Okay, so what's the p-value? Our p-value is 0.4180, like 42%. Okay, so for 27, our p-value is greater than alpha. We do not reject the null hypothesis. We do not have evidence. That the proportion is different. Okay, and that's that. Where did the 0.2090? This comes from the Z table. This is a lookup Z equal to negative 0.81 in the Z table. Yeah. Do I feel okay about all of this? Okay. In real life, have you ever seen or heard of an alpha larger than 10%? No, and actually, honestly, alpha 10%, I think people would laugh at you also. Just, I've rarely seen alpha bigger than 5% in real life. Like technically, like there's no law that states alpha has to be less than 5%, 5% or less. But in practice, I've never seen someone use alpha greater than 5%. So even when we say like alpha can be 10%, it's a little bit of a stretch. I haven't seen that in practice. So I would say alpha 5% and alpha 1% are a lot more common. And there's kind of actually a push to get alpha, yeah. So the kind of accepted standard is alpha is 5%. And there's kind of a push lately to get that number even lower. So to kind of think of alpha being 10%, I think people would scoff at that. Okay, we have just a couple more minutes. I don't know. I think maybe I can just kind of post the answers to the remaining questions, and I'll also include a little bit of work for the remaining questions, and you guys can go over them and look over that. I don't know if you had other questions per se. I feel like this gives a pretty good breakdown of what you can expect to see on the final. And yeah, these 20 to 25 calculation-based questions will be kind of similar in nature to these types of setups where I describe something and then I have maybe about 4 questions related to the to kind of that scenario there. Okay, and then review the other stuff for the conceptual questions, and I guess that's about it. If it's okay, I'll just post the answers to the remaining problems, and I'll make sure I post answers for kind of all of these practice problems that I've provided here. And so I hope that that gives you ample practice to do today and tomorrow. And with that, we will good luck as you study, and we will see you guys on Friday, either 10 a.m. or 10 p.m. Pacific time. And yeah, I guess that's it. I don't know. Let's see. Are we supposed to know all the details from the article? Or are they more general questions? Yeah, this is, so you're allowed to read the article, okay? All right, so it's not like, right, it's open note. You can, and open whatever. So if you need to open the article and read it, you can read it, right? You're not banned from reading the article, okay? And then I imagine you've already maybe have a notepad somewhere where you've written the answers to these things. So if you kind of refer back to that, then I imagine that should be good. Okay. All right. Oh, and thank you everybody for saying thank you. It's been a pleasure. Yeah. So thank you guys.